Hi everyone, today we are going to talk about thermodynamics for gate. Now before proceeding to this subject, we need to know some important points or the importance of this subject in terms of gate and in terms of real life also, which I have listed down here. Now before discussing this importance of this subject, let us focus on the mark distribution of gate. Now if you look at the mark distribution of gate, out of this 100 mark question, 15 marks come from our aptitude and English and 15 marks come from our engineering mathematics. And that remaining 70 marks covers our whole technical part, that is our whole mechanical subject. Now in this 70 marks or this technical part, this subject is going to play a very important role. So if we are to discuss the importance of this subject in terms of gate, the first point you need to know is that this subject is going to carry about the second highest weightage in that 70 marks, second to manufacturing engineering. Okay, now there is a reason for you to start 2 to 3 subject as a preparation subject, among which thermodynamics must be one, is that this subject is going to carry about 13 to 15 marks. And another reason for you to worry is that this subject is very easy scoring. If you listen to the class carefully, if you listen to the lecture carefully, you can easily score 11 to 13 marks out of this 13 to 15 marks. And in another point I will say that if you are to take my words, I will say that this subject is going to play the further subject to multiple subjects. That means if you understand this subject, if you understand the concept of this subject very carefully, you can understand the subjects like refrigeration, power plant engineering and some parts of heat transfer also very easily. So these are some important points of this subject in terms of gate. Now if you ask why do we study thermodynamics in terms of real life, how it is going to help in our real life. So this subject is going to give answers to your many questions. If you are to install some industry, if you are to install some factory, or if you are to install some project, the first question this subject is going to answer is that, is your project feasible? And if feasible, then up to what extent? That means this will give the answer of the feasibility of your project and the extent of feasibility of your project. Now second thing this subject is going to answer for your project is that what is the minimum input of energy you need to give to make your project work, to make your industry work. Okay, and the third thing this subject is going to answer you is that what is the maximum work output you are getting from your industry or from your project, and the efficiency of your project in terms of second and third point. Now if you consider these things, the fourth one, that is the most important point, it will give you the budget, it will give you the financial scenario of your project. If you are going to get a loss or if you are going to get a profit, this subject in terms of minimum input and minimum output will give you the answer very easily. So these are some important points of this subject, importance of this subject in terms of gate and real life. Okay, so after discussing this, let us start thermodynamics subject. Okay, so to know thermodynamics, we need to know that thermodynamics is a word consisting of two other words. One is therm and one is dynamics. Now what is therm? Therm is a Greek word which means heat, and dynamics means motion. Now motion is something which we get under the action of a force. If we apply some force, then only we get some motion, and then this whole phenomenon is known as work. If we say that if I am pushing an object and it is having a motion, then it is said that work is being done. So the main meaning of that word thermodynamics is going to be just an interaction between heat and our work. Now the aim of this subject is converting heat to work. Now if you question me, why do we need to convert heat to work? The answer would be, heat is a non-organized form of energy, and work is going to be an organized form of energy. So if you want to give some input in terms of non-organized form of energy, you obviously need to get the output as some organized form of energy. That's why we convert heat to work. Okay, so from the above discussion, if you are to know the definition of this subject, it will be, thermodynamics is the branch of science that deals with the heat and work interaction. And another thing that is additional is that it is also going to tell us about the effect of this interaction in the property of the system in which the interaction is going on. Now another point is that there is a property which distinguishes this subject from all other branches or all other sciences, is that temperature. Now if you see, or if you remember that in this universe everything has certain temperature. That is the reason why everything in this universe comes under the consideration of thermodynamics. Okay, the next thing we need to know is how to study thermodynamics. Now there are two ways of studying thermodynamics. One is microscopic and another one is macroscopic. Now microscopic is also known as statistical thermodynamics, and macroscopic is also known as classical thermodynamics. Now what is the difference between the two ways of studying the properties of a system? In microscopic thermodynamics, what happens? Our attention is focused on each and every molecule of the system to know the behavior of the system. For example, if there is a system and it is comprising of certain molecules, now to know the behavior of the system, we will take the readings of each and every molecule of the system. Now this is going to be very time consuming and very tiresome, so we generally do not use this. Okay, now before that, if you consider each and every molecule of this system, you are going to have crores of equations. You need to solve crores of equations to get the behavior of this system. So that's why we do not use this in general purpose. We use this concept in terms of some low density gases, only for some low density gases which are exceptions. Now in low density gases, what happens if we solve say low density, that means density is going to be mass by volume. Now if density is low, obviously mass is going to be less. If mass is less, that means the number of molecules within it will be less. So in such cases, only in such exceptional cases, we use microscopic thermodynamics. Now in macroscopic thermodynamics, what happens? Our attention is focused on a certain part of the total volume of the system, and we take the average behavior of this part to know the complete behavior of the system. For example, if there is a system, we will not go to the molecular level of this system. We will take a certain region in this system, and we will take the average behavior of this system and declare the behavior of this part is the average behavior of the complete system. And this is generally used other than this, because this is very much time consuming, and this is very much easier way to know the behavior of a system. Now there is another concept which you need to know, is concept of continuum. So what is basically this concept of continuum? Concept of continuum is nothing but it is a criteria of applying macroscopic view. It gives us the condition where we are eligible, where the system is eligible for applying the macroscopic point of view. Otherwise we will have to apply the microscopic point of view. This concept is going to give us the criteria. Now what is the criteria? This criteria is nothing but a minimum volume. It will give us a minimum volume where a certain change in the molecule, a certain change in the molecular behavior will not affect that much. Now this small volume will be given by this concept of continuum. Okay, so to understand this, you need to focus here. What happens is, in concept of continuum, we take a small system, and out of this small system we take a region whose mass is dm and volume is dv. Now if we take the density of this small part, we will see that the density is going to be dm by dv. And in concept of continuum, we make a graph between rho and v. Okay, now in this whole diagram, what happens is, if we take a small volume, suppose v1, if we take a smaller volume, you will see that even for a small change in molecule, the density is going to vary very highly. Okay, so for example, if we take suppose a small volume and there are certain molecules, what happens in this volume v1, if a molecule comes out of the system, then the density of this system is going to come down. So in this volume 1, this lower density will be here. And suppose in the previous part, a molecule from outside comes in, then the density is going to increase. Now the density, higher density will be here. So you will see that for a smaller volume, even for a small change in molecule, the density, the range of this density is going to vary very highly. Okay, now suppose if you are going to increase the volume, I have increased the volume to v2. Now for a bigger volume v2 I have taken. So you will see that in this part, the range of density change for a smaller change in molecule, whether it is coming out or coming in, this range is going to be smaller compared to the previous one. Previous one the range is here. Now next is here. Okay. Now in this way, if you are increasing the volume of the system, you will find that there will come a certain point where a small change, if you increase the volume and take a certain volume, suppose V dash, and there will be lots of molecules. Now you will see that even if a small molecule is coming out or coming into the system, you will find that there will be no such effect on the density. The range is going to become smaller, 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 and up to a certain point the range is going to be negligible, and that point, that volume is known as V dash. Now this concept of continuous is going to give us the V dash. If we have V dash, that means to apply macroscopic point of view, we need a volume which is equal to the V dash. Now V dash will vary from system to system. For a certain system there will be a certain V dash. Okay. Now this concept is going to give us the criteria, that is the V dash. So this is the minimum volume you need to consider to apply macroscopic point of view. To make the averaging, what happens in macroscopic? In macroscopic we take the average value. So this volume will make the averaging of this system very meaningful. So this is the saying of the concept of continuum. Okay, so as V dash gives us the minimum volume up to which the molecular effect is going to affect the average value or average behavior of the system. That's why if we draw a line through the V dash, the left part is called domain of molecular effect and this part is called domain of continuum. Here we can take the average value of the system and we can declare the behavior of the system. But before this, in domain of molecular effect, even a small change in the molecule or molecular property is going to vary the behavior of this region very highly. That's why we call it as domain of molecular effect and call this as domain of continuum. The next topic would be to know what is thermodynamic system, thermodynamic surrounding and thermodynamic boundary. Now what is a system? System is a region in space or a region somewhere our attention is focused on. That means if we are doing some experiment, if we are taking the readings to know the behavior of that part, is known as a system. And everything surrounding this system is going to be known as a surrounding. And what is boundary? The thing which separates this system from surrounding is known as boundary. For example, if you see this figure, if our attention is focused on this part surrounding by black ink, or we want to know the behavior of this part, then this is going to be our system. This is the part where our attention is focused on. So this is going to be our system. Now everything around this, everything external to this is going to be known as surrounding. Now this black thing, the thing which is marked in black ink, is going to act as our boundary because this is separating the system from the surrounding. Okay. So thermodynamic boundary is again going to be divided into two parts. One is real and one is imaginary. Now what happens in real? In real boundary system, whatever the thing which is separating the system from the surrounding is going to be tangible or something we can touch. For example, if we take a tank or a rigid tank full of air or water, then the walls of this tank is going to act as the boundary between the system which is inside the tank and between the surrounding which is going to be outside the tank, and the walls of this tank is going to act as the boundary of between the system and the surrounding. Now these walls are something which are made up of some matter and we can feel and we can touch it. So this is going to be a real thermodynamic boundary. But what happens in imaginary boundary? We need to imagine the boundary. We know that something is passing through this region, but there is something which we cannot touch. For example, if we take a room, then the open space in between the door and this window is going to act as an imaginary boundary. If we open the window, we can easily see that from the outer atmosphere air is coming into the room or air is going out of the room. Then the open space in between these windows is going to act as an imaginary boundary, and this room is going to act as the system and outer atmosphere is going to act as a surrounding. In between them, mass transfer or air transfer is going through this imaginary boundary with the region which is situated in between the windows. So that is going to act as imaginary boundary. Now again, real boundary is again divided into two parts. One is fixed and one is moving. Now what happens in fixed? None of the boundary moves. none of the boundary moves and everything will be rigid. And in moving, what happens, this is the type of the boundary which moves. For example, if we take the example of a fixed boundary, you can take the example of again the rigid tank, where none of the boundary is going to move. And if you want to take example of moving boundary, then it is going to be our piston cylinder arrangement. If we take a piston and a cylinder, the piston is one of the boundaries which is covering the system inside the cylinder. Okay. Now if the pressure of the air increases, automatically the piston goes through the outer side. Then this piston is going to be acting as a moving boundary. Now this moving boundary is necessary to get work output. If we want to get some work output from a system, then at least one of the boundaries must be moving. This is the point we are mentioning here. Okay. In terms of heat transfer, thermodynamic boundary is again divided into two parts. One is adiabatic and one is diathermal. Now we all know adiabatic boundary means that boundary doesn't allow any heat to flow through it. And in diathermal, what happens, it allows heat to flow through it. Now if you remember the concept of heat transfer, you will see that heat flux or heat transfer per unit area holds the formula of temperature difference by thermal resistance. Okay. Now in adiabatic case, thermal resistance acts as infinity. That means there will be infinite resistance to heat transfer. So that is the reason why heat flux or heat transfer per unit area is going to act as zero or nil. None of the heat is going to transfer through this boundary. Now in diathermal, the complete opposite happens. What happens in diathermal? If we take heat flux or heat transfer per unit area as del T, temperature difference by thermal resistance, here thermal resistance is totally zero. That means it will allow all the heat that will come to the boundary, it will pass all the heats through it. So that's why the heat flux or heat transfer through unit area is going to be infinite. Okay. The next thing we need to know is what are the types of system. Now there are three types of system. One is closed system, one is open system, and one is isolated system. Now we will see all these systems in details. So for that, let us first take the example of closed system. Now what is a closed system? Closed system is a system the boundary of which does not allow any of the mass interaction, but it may allow some heat transfer or work transfer, that is energy transfer can take place, but mass interaction doesn't allow at any cost. Okay. So that's why I have written dm is equals to 0. That is, change in mass of the system is going to be 0. dq is not equals to 0. If we supply heat, then it may transfer heat. If I supply work or if I want to take out work, then it may supply work. It doesn't mean that always a closed system passes heat energy or always a heat system gives out work. If the conditions are such that we can take out work, then it will allow us to take out the work. If the condition is such that if we give heat, then it will take the heat. That is, energy interaction it will always allow, but mass interaction it will never allow. So to understand this, we have taken two examples. First one is example of rigid tank. Now what happens in rigid tank is the mass interaction is going to be 0. A rigid tank means none of the boundaries is going to deform. None of the boundaries is going to deform. So if we give heat through the boundary, the heat interaction is going to occur, but what work interaction is not going to occur. What is the reason? Because a moment ago I have said that if you want to get heat output or heat interaction, one of the boundaries must be moving. So in rigid tank, none of the boundary is going to move, so work interaction here is going to be 0. Now in the second example, we have taken a piston cylinder arrangement. Now what happens in that, the mass is going to be constant inside this arrangement. Okay. So mass interaction is going to be completely 0. If we give heat interaction is also going to be there. If we give heat will pass through this boundary. But if we give some heat, the internal energy of this system is going to increase. And to maintain the pressure, the piston will go away from the system, so giving us some work output. So if we take the work output, that means there is going to be work transfer or work interaction. Okay. So these are the two best examples of closed system. One of which shows only heat interaction but no work interaction, and this shows both heat interaction and work interaction. Okay, so in the discussion of closed system, we have said that mass is going to be constant at any cost. So we call closed system as control mass system. But in open system, what happens is, in open system everything gets allowed. That means all mass interaction also can take place, work interaction also can take place, heat interaction also can take place. In these conditions, we take one certain thing common, that is volume. We take the volume as constant. Okay, so for that I have written that dm is not going to 0. That means mass interaction is going to be there, heat interaction is also going to be there, and work interaction is also going to be there. So to make this understand very clearly, we have given an example here. Okay, so this is an example of an open system. Now one thing you must remember, that to be an open system, one or few of the boundaries must be imaginary. Only imaginary boundaries is going to give you some mass transfer. For example, if I take a room as an example, if you open the window, so in window plane, that is in between the borders, whatever the plane is there, no matter is going to be there. Okay, now this is an imaginary boundary. In this empty plane we have to imagine a boundary, and this boundary is going to give us the mass transfer. Okay, in our example, dm is not going to be 0. That means change in mass is going to happen in this region, or in that case in this region. Here we must have imaginary boundaries. Okay, only imaginary boundary is going to give us the facility of mass transfer. So in here there are two imaginary boundaries, and if I hit this total system, then there also is going to be a heat transfer. And if we insert a shaft here, let us I have drawn here a symbolic turbine. Okay, so mass is coming out from here and going out from here. If we hit this, then certain work output or work input is also going to be there. That is heat interaction through this shaft is also we are going to get. Okay, so this total sum is going to give us an open system. Now what are such examples of open system? You can take examples of turbine, compressor or pump, etc., where mass interaction is constantly going to be there, but the volume of our consideration is going to be constant. So this is the reason we call it as control volume. Okay, okay, in isolated system, the system is not going to allow any of the things. No mass transfer, no heat transfer, no energy transfer. That is, this isolated system is a system which is not going to allow any of the thing. Okay, so I have written here no heat transfer, that is dq is also going to be 0. No work transfer, that is dw is also going to be 0. No mass transfer, that is dm is also going to be 0. Now if you want to take a perfect example for insulated or isolated system, we are going to take completely insulated rigid tank. Okay, now for rigid tank it is not going to give any work output because none of the boundaries will be moving, and for a rigid tank, as none of the boundary is going to be imaginary, so it will also not allow any of the mass transfer. And by insulating this whole rigid body, we are going to give our heat transfer completely 0. Now as we made our body insulated, the heat transfer is going to be completely 0. And the things I have explained now, rigid tank is going to give dw is also equals to 0, and mass is also going to be constant. So this is the perfect example for isolated system. Okay, the next thing we need to know is what are thermodynamic properties. Now what do we mean by properties? Properties are the characteristics by which a system is going to be identified. Okay, now it is a characteristic by which a system is going to be identified. Now there are two types of properties. One is intensive properties and one is extensive properties. Now what happens in intensive properties? Intensive properties is not going to get dependent on your size or mass of the system, whether it is 100 kg, whether it is 1000 kg. If the size is going to get bigger, the properties of the systems are not going to change. So some of the examples of these kind of properties are pressure. Okay, now if you take a room full of air, if you divide this room also, then in both these parts also pressure is going to get same. That is, it does not depend on the size of the system. Similarly, there are temperature, velocity, viscosity, thermal conductivity and density of the system. Okay, now another one is extensive properties. What happens in extensive properties? In extensive properties, the properties are going to depend on the extent of the system. Okay, now if we increase the size of the system, now suppose this is a room, and if we this size becomes double, obviously this mass is also going to get doubled. So mass is going to be a property which depends on this extent of the system or size of the system. Now some of the examples are going to be mass, volume, energy, enthalpy. These are the properties which are going to get changed drastically if we increase or decrease the extent of the system. Okay, so to understand these extensive and intensive properties in a better way, we have given some example here. So let us focus. Suppose in figure 1 we have taken a room full of air, and in this room full of air these are the properties which are going to consider. So in a room full of air, whatever the mass of the air, it is going to be, let us denote it as m. Whatever the volume may be, we have taken it as v. Whatever the energy present inside this room is going to be E. The temperature of it is T, pressure P, and density is going to be rho, let. Now in second figure what we have done is, in that room, in between this room we have drawn a rigid boundary. We have made a rigid boundary so that the total room now gets divided into two equal compartments. Okay, now what happens is, whatever the mass there was in the room in figure 1, after making these two equal compartments, this mass is going to get divided into two equal parts. One is m by 2 and another one is also m by 2. Similarly, the volume is also going to get divided into two parts. Okay, v by 2 and v by 2. Eventually, this energy is also going to get divided into two parts, E by 2 and E by 2. But the temperature is not going to change whether we make it 2 compartment or 100 compartment. The temperature of both these compartments is going to be same. Similarly, pressure is also going to be same. But in case of density, what happens? Now the new mass becomes m by 2, new volume becomes v by 2. Now if we make this ratio, then 2 by 2 gets cancelled and the ratio becomes same, m by v only. That means the density is going to be same as before, even if we make this compartment. Okay. Now what happens is, in these 6 properties, these are the 3 properties which are going to depend on mass. That means we have seen here, if we make a compartment and make this size of each system half, these properties are also going to get half. So as these are depending on the extent of the system, we can name these properties as extensive properties, and these are the properties which are going to be intensive properties. Because even after we have made these systems into half, these properties which were present before has not changed themselves even after the division into half. That means these are the properties which does not depend on the size or mass of the system. Okay.